Modern artificial intelligence can now write software, analyze complex legal documents, and hold conversations in hundreds of languages. We are constantly told these systems are taking early steps toward artificial general intelligence. But beneath all those complex capabilities lies a much simpler test, one you could give to a kindergartner. Can the AI identify the complete set of building blocks from which a language is constructed? In other words, can it recite the alphabet? For English, every advanced frontier model passes with ease. They score a perfect 26 out of 26. But we have to ask, did the model actually read millions of English sentences and independently deduce the exact 26 letters used to build them? Or did it simply memorize a list it saw repeatedly during training? The truth is, English provides a contaminated experiment. The A through Z sequence has been published everywhere, in classrooms, dictionaries, and training materials. The models had access to the answer key long before we ever tested them. To run a clean experiment, we need a language where the AI has read plenty of text, but where the foundational alphabet has never been formally published online as a single complete list. We find exactly that condition in many Bantu languages. These models have encountered names, sentences, and texts in these languages, absorbing thousands of examples of their use in the wild. Instead of 26 individual letters, the operating alphabet for a Bantu language is what linguists call a full syllable inventory. This is a complete, bounded set of specific consonant and vowel combinations locking together to form the natural building blocks of speech. This brings us to the L26 benchmark. It asks a deceptively difficult question. Given all the text a model has absorbed, can it examine the corpus and independently identify every single legal native syllable? Without a published cheat sheet to fall back on, the model can't rely on memory. It has to look at the patterns it has learned and discover the hidden rules of the system entirely on its own. This bar chart shows the results for the newest generation of frontier models, including GPT-5.6 and Claude. Against the perfect 26.0 for English, their performance on the blind Bantu syllable test plummet. They average scores like 5.1 for Bemba and 6.1 for Luvale. When forced to deduce the structure without a map, their internal uncertainty becomes visible. They omit real syllables, they mix native structures with borrowed ones, and they invent entirely fake combinations that merely look plausible. Yet these same models can still translate phrases and generate convincing sentences in these languages. They have achieved surface fluency while completely missing the structural foundation underneath. To find out why, researchers ran a second experiment called a scaffolded test. This time, they handed the models the fully calibrated list of syllables, the equivalent of an alphabet chart on a classroom wall, before asking them to process the language. A moment of wonder. The results flip. Once provided with the declared standard, the models immediately achieve near-perfect or completely perfect scores across the board. The systems are completely capable of working with these linguistic rules. They just lacked the chart. Pouring unstructured data into a larger neural network does not automatically generate a foundational map. This is an infrastructure problem, not a capability problem. These missing foundations carried serious real-world consequences. Bantu languages are spoken by hundreds of millions of people across Africa. When AI systems fail to understand their structural building blocks, the impact is felt every day. Speech systems misunderstand local speakers. Translation quality drops. And public information tools deployed in medical, legal, and financial sectors become completely unreliable for the people who need them most. The fix requires what researchers call declared infrastructure. An organization called Bantunomics has started closing this gap, explicitly mapping and releasing the exact full syllable inventories for 459 separate Bantu languages. This calibrated standard gives the AI a way to filter the noise. It teaches the machine to separate native linguistic structures from colonial spelling errors, internet typos, and imported technical terms found in raw data. Scraping the internet for raw text provides only a partial picture of a language. Real equity in AI depends on the deliberate creation and integration of these exact human-verified baselines. Tech companies frequently claim their models are approaching artificial general intelligence, pointing toward the ultimate goal of the Einstein test, building a machine capable of independently discovering hidden laws of physics. But discovering general relativity is an incredibly complex undertaking. The L26 benchmark, by contrast, is a small, finite, mathematically scorable task with a closed answer key. We cannot claim a system possesses general intelligence if it masters the English foundation but fails to recognize the equivalent building blocks of Bemba or Luvale. The standard must follow the function, not the prestige of the language. It is time to stop inferring a machine's intelligence from its surface fluency. We need to test its capacity for structural discovery directly, using objective, measurable benchmarks. Before humanity trusts artificial intelligence to uncover the universe's secrets, the machine must first prove it can independently discover the alphabet.